We continue to talk about the sun, folks, and the layers within it. Let's begin by talking about the photosphere. Now, the photosphere is what you would see if you took a photograph of the sun. This is the yellowy white face of the sun that you and I see all the time. Now, when I look at the sun, it looks like it is a perfectly smooth surface, but it's actually not. It is a hot, churning, violent ball of plasma. And if you look at it carefully through filters so you can get past all the brightness of the light, you will see that the sun itself is very bumpy. And that bumpiness on the sun is called granulation. This is the texture on the surface of the photosphere, and it's due to convection currents of this hot plasma coming up from deep within the body of the star. These convection currents are going to bring hot plasma up from the surface. The plasma is going to cool slightly and return deep within the star. Now, whenever there is one of these rising currents and then retreating, you get a convection current bubble at the surface. And this picture on the left is more realistic. The one on the right, of course, is an illustration, but it gives you an idea of size. This is the entire North American continent, and one of these convection current cells can be as big as maybe a third of the North American continent. So we're talking about huge, huge features. I really want you to understand that the sun is not a quiet thing. It is a violent, churning ball of plasma that is constantly upswelling, lots of matter and lots of heat coming to the surface, and then having that plasma sink back down to colder layers. One of the other ways that we can actually map this churning plasma on the sun is using a process that's called Helio Seismology. Helio, of course, Greek word for sun. Seismology is how we detect earthquakes. So this is basically sunquakes. If we're going to detect earthquakes on the Earth, we do this by putting up sensors on the planet. Well, we have never landed something on the sun because if we did, it would be burned to a crisp immediately and it would not send any data back. So how do we detect earthquakes or sunquakes? The way we do this is with the Doppler effect. If something happens to be moving towards us, the frequency is going to go up. And if a light source is going away from us, the frequency is going to go down. So if we look at various parts of the sun with the Doppler equipment to actually measure slight differences in wavelengths from the light emitted from the star, we see huge areas of the sun that are, like this is red, indicating that is a place that's kind of like a well. Large quantities of plasma are sinking down into the sun. This blue area in the Doppler shift is a big bubble. So if you could look at the sun, it would have areas that are coming up and swelling and areas that are moving down or receding. But the sun is so incredibly huge and so far away that to our normal everyday perspective, it looks nice and smooth. But if you could get up close to it, it's going to have ups and downs and peaks and valleys due to the up and down motion of the plasma. The chromosphere. Now, chromos means color. And this is the colored ring that we see around the sun during an eclipse. You cannot see the chromosphere with your naked eye. It's just impossible due to the brightness of the star. But whenever we look at an eclipse, we see this pink area. And that pink area is the chromosphere, the colored sphere of light that actually circles our star. Where does the chromosphere come from? Well, as I mentioned in the last slide, the star is this big upswelling of plasma coming from deep within the sun. That's the charged gas. And then sometimes this charged gas is moving upward at such a violent, fast speed that it will actually break free of the surface of the sun before it falls back down again. And those areas where this upswelling of plasma is above the surface of the sun, that is the chromosphere. Now, why pink? Well, pink is an indicator of hydrogen gas. A lot of nebula and things we see out in space are pinkish in color because of presence of hydrogen. Earlier in the course, we actually looked at some gases and the spectra they produce. And if you look at an entire tube of just hydrogen, it's going to look sort of Pepto-Bismol pink. And that is a big indicator of hydrogen gas. From our perspective on Earth, this looks like a very thin layer. Keep in mind, as I mentioned, the sun is very, very big. So this could be 10,000 kilometers, and we're talking maybe 6,000, 7,000 miles thick. So this is really, really tall if you and I were standing next to it, but good thing we're not because it's really hot up there. When I was a kid and would draw the sun, I drew it like this. I always drew little sparkly bits coming out from the side. Well, unbeknownst to me, when I was a kid, I was drawing spicules. Okay, say that word with me, spicules. Now, what spicules are, these are the spiky, sticky out parts of that chromosphere. Chromos, this is that colored layer of the sky, of the star. Where do they come from? They are a result of these big convection currents. As the plasma rises, it doesn't just stop. It actually goes above the surface of the sun and then falls down as it cools. And this is all done by hot stuff rising and cool stuff falling. And that causes these spicules, which is this up and down spikes on the side of the sun. At any moment in time, there could be 500,000 of them around the sun. They're not a permanent feature. Each one's going to last only 5 to 15 minutes. They move and oscillate very, very quickly. This is a beautiful picture of the actual spicules themselves. The dotted line represents the actual surface of the sun, and then these are hot plasmas that are rising thousands of miles in above the solar surface as part of these convection currents. Another thing you're going to see on the chromosphere is plage. Now, here's another word I'd like you to say after me, which is that word plage. Plage rhymes with the word snaz, and that's why I have a picture of the old entertainer Jimmy Durante, because his nickname was the snaz, and that's to help me remember how to say this because I am not fluent in French. But plage is a French word that stands for beach sand. If you go to a resort, you go to the seaside and you would see beach sand, and the beach sand would look quite white and pristine compared to the background. Well, astronomers started looking at the sun through various filters, and what they found was some areas looked lighter. And these lighter areas of the star itself, those were the plage. They actually happen to be hotter regions. So for some reason, as the plasma within the sun is churning upward, these are hot regions of the star itself. These are typically found, plage are typically found near sunspots. Sunspots appear darker. Here is a sunspot. There's a little one. There's a little one. Here is a little one. So there are some sunspots that will appear a little bit darker, and they are nearby plage, which are areas that appear lighter. Helium. Helium, I know you've played with helium somewhere in your life. You've had the joy of having a helium balloon. Helium is named for, of course, the sun god Helios, and it was discovered first in 1868, and it was discovered by astronomers. Now, astronomers were actually looking at the solar spectrum, the light that was produced by our star, and they found some spectral lines that were very, very strong, indicating there was a lot of whatever it was, there was a lot of it in the sun. And they named it Helios because this was an element found in the sun. But it had not been discovered on planet Earth back in the 1860s. About 40 years later, in 1908, it was actually discovered in labs on planet Earth. And that's one of the things I adore about science, is science discovers something and predicts and says, hey, there's another element out there. We're going to name it for the sun because that's where we found it. And then much later, we find it on Earth. When science can predict something and then it comes to pass, that is good science. All right, folks, that is going to end this section. We're going to come back next time and we're going to talk about the corona.